This video is going to cover the cantilever method. For this method, the assumptions are pretty much the same as they were for the portal method, in that halfway across the girder between a fixed and fixed column is going to be zero moment, and again halfway up between fixed and fixed ends is zero moment, and there's zero moment at a pin. So the full height, if it's pin fixed, will have zero moment at the pin. So those assumptions are all the same, but how cantilever differs is that the cantilever method also assumes that the stresses in the columns are proportional to the distance from the centroid of the cross-sectional areas of the columns at the same floor level. So in this example, all of the columns have the same cross-sectional area, and we're only looking at one bay, though we do have two whole stories and two different point loads there acting on the left. So the first thing that we're going to do is we're going to make a cut. So first thing that we're going to do is kind of cut through here. We're going to cut right through G and I and make a little free body diagram here. So we're making our cut. Again, halfway up is going to be where that zero moment location is located. And we're just going to kind of draw a little picture. We've got normal forces coming out. And I did draw one of them up because remember about the difference here to the centroid of the cross-sectional areas. Because they are the same cross-sectional area, the centroid is going to be directly in the center, and the stresses are going to be proportional to the distance. So if I could actually hit that midpoint a little bit better. We have a stress over here on the right that's going to be going up. So this is stress. This is going to be I at point I. And then over here we have stress, and this is point G. So we had our normal force. This is normal I. And we had our normal force over here. This was normal G. And what we know is that the stresses are proportional to their distance to the center, and that centroid of the area for the cross-sectional areas is 3 meters, since it's the same on both sides, and this is 6 meters wide. So again, 6 meters, and we do also have a point load over here that's 15 kilonewtons. And we are halfway down that column, so if the whole column there from E to F is 4, then halfway down is 2 meters. So we have a little free body diagram, and what we're going to do is start off by talking about similar triangles. We have the similar triangles between our two stresses. So we're going to write that out. We have that stress G to the distance to the center there. X bar is 3 meters. And similarly, the triangle for stress I is also a distance of 3 meters. Which does mean that stress G and stress I are equal to each other in this case. Now, stresses really don't help us at all, right? We're talking forces, so we do need to turn these stresses back into forces, and do recall that a axial normal stress is equal to the normal force divided by the area, and all of our cross-sectional areas are the same. So this is just normal at G divided by the area of the column, which is equal to the normal at I divided by the area of the column. The areas are the same, so they cancel out. So therefore, the normal force at G is equal to the normal force at I. But do notice the direction change here. We have normal force at I going up and normal force at G going down because of how our triangles are drawn. So what can we do with this information? Well, now that we have our normal forces in terms of one another, what we can do is try and solve for one of them. So in order to do that, we can't really sum the forces in the y direction because there's two forces. Summing in the forces in the x direction doesn't really get us what we want. We want the normal forces, not the shear. And there's technically shear at those joints. Maybe best to draw those in, right? We have shear here at I, and we've also got shear at G, and we don't want any of those, so technically there's 4 unknowns here, and we really only want one of them. So in order to isolate it, what we're going to do is take a moment about a point that's going to cancel 3 of the 4 of these. So our shears are both going in the horizontal direction. Both of them, though, are 2 meters down. And if we take a moment about a point where one of these normal forces is, then it'll cancel that. So we're going to go over here and take a moment about this point. We'll call it P. So if we sum the moments about P and set it equal to 0, taking counterclockwise to be positive, we have our 15 kilonewton load. So he's 15, but he's going in the negative direction, so negative 15 kilonewtons times a distance of 2 meters. Then, well, shear at G is canceled out, normal at G is canceled out, shear at I is canceled out. All of those are going to be going in the parallel or perpendicular direction, whatever you want to call it. They're all acting at point P. So the only other force that we have is the normal force at I. And the normal force at I is going to be going in the positive direction. So we have plus normal of I and his distance of 6 meters. So we have 15 times 2 on the one side and then 6 on the other. So normal of I is equal to 5 kilonewtons. And because of our handy-dandy little over here equality, we're also going to show that normal at G is also equal to 5 kilonewtons. So these are both positive values, so we are literally just looking at the directions of those guys. So normal at G is going down, normal at I is going up, for what it's worth. Now that we've found these, we can actually make another cut. So remember that at the center here, there is 0 moments. We're going to make a cut again right there, and we're going to isolate the left side. So on the left, again, we're going to have 3 meters over and 2 meters down. We have our point load of 15 kilonewtons. We just found normal of G going down, 5 kilonewtons. We also have shear at G. Then this spot here at the top that we cut into is H technically. So we're going to have shear at H, and we're also going to have normal at H. So at this point, the way to solve the problem is very, very similar to the portal method. We're going to try and make cuts at spot where there's 0 moments to then try and make another cut where we can isolate the internal moments at the corners. And if you recall from the portal method, the only guy we actually need to know is the shear at H. That's going to create the moment at the corner point over here, the corner in this being E. So if I want to find the internal moment at E, I need to find the shear at H. Well, looking at my free body diagram, the best way to go about doing that is to simply sum the forces in the y direction. So if I sum the forces in the y direction, I've got 5 going down, I've got VH going down also, so shear at H is going to be equal to negative 5 kilonewtons, which means shear at H is actually going up. So my next step is to then have a free body diagram where we've got shear of H, he's actually going up. That's what we just found. We also have normal at H. So we're making a cut right here, technically, to expose the internal forces at E. So we've got shear, normal, and moment at E. And just like we did before for the portal method, all we have to do is sum the moments about that corner point and set it equal to 0. And moment at E is going the wrong direction, so negative moment at E. And then we have plus shear, which again was 5 kilonewtons. We did change the direction of the arrow there to match. So that was 5 kilonewtons going up. So that's going to be 5 times his distance of 3. So the moment at E is equal to 15 kilonewton meters. So now that we've found that, we can move on to our next spot. Recall that the problem statement wants us to find the moment diagram for A, F, and E. So we're actually drawing the moment diagram for that vertical member. Kind of interesting. A little bit different from what we've done in the past. So we're going to move on to F. So again, it's going to kind of function the same way. We're going to make cuts at areas where we know zero moment. And that's halfway up the columns and halfway over. So again, this would be 3 meters, and we have 2 meters and another 2 meters. What we did know normal at G, and if normal at G is going to be 5 kilonewtons in tension, and that makes it 5 kilonewtons in tension on the other side. Again, also shear at G. Then we cut into the horizontal, this is K. So we have shear at K. We also have normal at K. We've also got our normal at J. We have our shear at J. Well, based on this information, don't forget we have our point load acting on our corner here. So that's 30 kilonewtons, and there's really nowhere that we can solve. So let's go back to our big free body diagram that we've got here. Let's actually make our cut here. If we make a cut here, we can analyze the whole member, and we're going to find our normal force at J. That's what we want to find. So let's make that, and once we find normal force at J, we can do what we did before. So this time we've got our 4 meters. This is 2 meters down here. We've got our normal force. This is going to be normal force at J. And again, we've also got normal force at this side's going to be L. Remember, again, the cantilever method assumes that stresses are proportional to the distance from the cross-sectional areas. So this is going to be stress L and stress J. Since it is the same area for both of those, we already found what's going to happen, right? If we just look back up at the top, what did we find? We found that since the cross-sectional areas are the same, the stresses are the same. Since the stresses are the same and the areas are the same, the normal forces are the same. So we're going to use the same logic that we did over here. So again, just to rewrite that out, we have stress of J is to 3 meters. That's his distance to the center right there. And we've also got stress of L is equal to 3 meters here. Those are the similar triangles that we've got going on, right? 3 meters and 3 meters. So we did similar triangles. Again, we found that stress of J is equal to stress of L. And remember that a stress is just a normal force divided by an area. So we have normal force of J divided by the area of the column, and we have normal force L divided by the area of the column as well. So since the area is the exact same, we also found that normal of J is equal to normal for L. Now again, remember in this free body diagram, there's also shears. So this is shear at J, and this is also shear at L. And we now have, again, 4 unknowns in our wonderful free body diagram. So if we want to get rid of all of that, what we're going to do is take a moment at a spot that will get rid of 3. So just like before, we're going to take the moment about this point. We'll call it P again. So if we take the moment about P, neither of the shears are going to act and create a moment at P, and neither is the normal force at J. So if we sum the moments about P and set it equal to 0, taking counterclockwise to be positive, what are we going to get? We've got 15 times a distance of 6 meters, right? Because he's 4 plus 2, got to go the whole way there. And he's going to be going the negative direction, so negative 15 times 6. And then we've got our 30, and our 30 is also going negative, so minus 30 times his distance of 2. Then we've got NL times a distance of 6. He's going to be going positive, so plus NL times a distance of 6 meters. So we're going to find that the normal force at L is equal to 25 kilonewtons. And of course, if the normal force at L is equal to 25 kilonewtons, then the normal force at J is also 25 kilonewtons. So normal force L is going up, and normal force J of 25 kilonewtons is going down, as per our diagram that we have drawn. So moving back over here, this is 25 kilonewtons. Again, we can solve for our forces in the y direction now. Since we have our normal force J going down, that leaves us with the one and only y direction, shear at K. So if we sum the forces in the y direction and set it equal to 0, we got 5 going up, we got 25 going down, we've also got shear at K going down. So shear at K is going to be equal to 30. Right? Nope. Just kidding. Yep, 20. 5 minus 25, so it's at 20. 20 kilonewtons there. And he's actually going to be going up. So if we break that member open, we've got 3 meters. We just found shear K. So shear at K is 20 kilonewtons, we said going up. Technically, there's the normal at K. And we cut right before we hit that column, so we're cutting right there to try and open up what those internal shear normals and moments are. So we have internal shear, internal normal, and internal moment. This is moment at F. Moment at F. So if we sum the moments about F and set it equal to 0, taking counterclockwise to be positive, we have moment at F going the wrong way, and then we have our 20 going the correct way times a distance of 3. So moment at F is equal to 60 kilonewton meters. And we could keep on going, but effectively you're just looking at the other end of the column, so we can stop right here and draw our moment diagram. So if we come back up to the top, if I want to draw my moment diagram, we found that the moment at E is equal to 15. So how that's going to look, so we got 15 here. Remember, he's going to cross the 0. So this is 15 kilonewton meters, crossing that 0 there, which also means that this is negative 15 kilonewton meters. If this is our positive and negative for our moment diagram here. And we said that the moment at F was a grand total of 60 kilonewton meters. So that means that the distance from here over, that's going to be a grand total of 60. So this is technically going to go back up. And 60 minus 15 is going to be at 45 kilonewton meters. And then again, he crosses the 0 at that midpoint. And he comes back down over here to negative 45 kilonewton meters. So that is technically what our moment diagram looks like for member AFE using the cantilever method.